Hi, my name's Tom Wagg. I recently finished my undergraduate degree and I'm really excited to be here talking at the LISA Symposium. The work that I'm presenting is something that I've been working on since the past year of my undergraduate degree, and I've been working with Broekgaarden, Selma the Mink, Stephen Justin, and the entire COMPASS team to try and work out how many black hole neutron star binaries will be detectable with LISA. And I should emphasize that this is a work in progress and I'm fairly new to the topic, so please do let me know if I get any of the citations wrong, and sorry if that's the case. And I'd love to hear any questions, comments, or feedback that you have, and so here's my email in case you want to reach out. Great. So, I think the best place to start any talk is at the end. And so, what we're trying to find is how many black hole neutron star binaries will LISA detect, and I'm going to skip to the end and tell you that LISA is likely to detect a few black hole neutron stars. The result is actually strongly dependent upon model assumptions that we find, and also I'm going to show that we could in principle detect them all the way out to the Andromeda Galaxy, which is quite exciting. So, first a brief introduction into the topic. Why exactly are we interested in these black hole neutron stars? Well, they're actually very interesting objects. So first of all, they of course come from the death of two very massive stars, and so we get a much better insight into the endpoints of massive stars, which is still quite unclear. In addition, we don't really know exactly how they form, and so there's several different formation channels that could lead to a black hole neutron star, and these would lead to a different number of detections in LISA. So when LISA comes along and actually finds a certain number by the end of it, then we can either rule out or say with certainty which formation channel is the best. It's also very useful for measuring the Hubble constant. So often people suggest the use of double neutron stars for measuring the Hubble constant with gravitational waves. But with the added mass of a black hole neutron star, you can actually see even further, and so it can be useful for this as well. Additionally, if we get lucky and the neutron star happens to be a pulsar, then we can actually use the object for testing general relativity. And so you can see there's lots of different varied uses for these objects. They're quite interesting. But why exactly do we want to detect them from space and with LISA? Well, I'm sure that all of you watching this probably know that LISA is focused on the millihertz frequency band. And so this means that we're going to detect the inspiral of these things rather than the merger. And so we're looking at a completely different population, which can be quite interesting. Also, for stellar mass binaries, we're really only going to see them within the local group. And so we can get a much better grasp on our local environment and a much better understanding of what's close to us, since we don't really know that exactly right now. Another interesting thing is that for a ground-based detector, by the time you see it, you're seeing the binary very close to merger. And so by that time, the gravitational waves have circularized the binary. However, in inspiral, we could potentially detect them when they're still eccentric. And this can be very interesting, as I'm going to show a couple of slides later. And so how exactly do we think they are formed, at least for now? The main channel for this really is isolated binaries. So these are stars that are born together in a binary, they evolve together, they both go through some sort of supernova, and then they have a common envelope phase where they're both within one dense kind of cloud of gas. And so the added friction from that as they're spiraling gets them very close together. And this allows them to merge within Hubble time, and so pass through the LISA band and become detectable. So this is really the favored scenario for black hole neutron star formation. There are other formation channels, such as dynamical formation that happens within globular clusters, but recent studies have shown that the merger rates for these are quite low, and so we don't focus on those. There have also been several similar studies to the work that I'm doing. Lots of them are listed here, and they're generally focused on other double compact objects like double white dwarfs or binary neutron stars. And some of the most similar that I'd like to highlight are Mike Lau's work, where he also uses COMPASS, the same as me, but he focuses on binary neutron stars instead of black hole neutron stars. And then there's Katie Breivik, who does have estimates for black hole neutron stars, but she uses the cosmic code. And so these two are very similar, and you should check out their talks here. They're also at the symposium. So now let's go through exactly how I get to my results. So the process is sort of a three-step sort of thing, where firstly we take a series of binaries and evolve them into black hole neutron stars. We then simulate the galaxy, put them in particular positions, and then finally work out whether they're actually detectable by LISA. Now my work in particular focuses on the latter two, where the first one is done by Broekgaarden, and you can see that in her upcoming paper. And what exactly she's doing is taking a series of stellar binaries and evolving them and working out which ones become black hole neutron star binaries. And she's doing this using a rapid population synthesis code called COMPASS, which is now freely available. You should check it out. Now for these models, for the fiducial model, the physical assumptions that go into it are all listed here. And I'm not going to go through each one by one right now, but it's in the slides. And so if you have a question about it, feel free to let me know. Now more onto exactly what I do. So as output from Flo's simulations, I end up with a series of parameters where for each binary I know the mass of the black hole and neutron star, the separation between the two, the eccentricity of its orbit, and the amount of time it takes for it to go from being a stellar binary to a double compact object. And then using the top ones, I can work out the inspiral time, or how long it's going to take to merge. Now, in order to work out whether something's actually detectable, we need to know where it is, so that we know how far away it is for the detection. And we also need to know when it was born, so we know how long to inspiral it for, to see how much the separation has decreased over time. And so for this, we use the Frankel model for simulating the Milky Way, particularly because it has a metallicity distribution in addition to positions. It was modeled specifically on the age metallicity distribution of the apogee red clump stars in its 12th data release. And we supplement it also with the vertical distribution from Macmillan 2017, since they assumed a flat disk in the Frankel model. So as we can see on the right here, I've plotted a side-on view and then a view from above of the galaxy. And if you focus specifically on the side-on view, you can see the colors are the metallicities, and these darker colors on the edges, these very low metallicity, and then these bright colors in the center are high metallicity. And so you can see a bit of a distribution there. So before we get into the main results, let's do a brief survey of the problem. So hopefully this looks familiar, and this is the LISA sensitivity curve. And the general idea of this is that if you plot the strain of the binaries on this plot, then the height above this curve should be equal to the signal-to-noise ratio. And so if we take a typical black hole neutron star with these parameters and plot it at 3 different distances, which are hopefully familiar to you, at the Milky Way center, the Magellanic Clouds, and the Andromeda Galaxy, you can see roughly where they're going to lie on this LISA sensitivity curve. You can see that they're all above the curve, and so they do have a signal-to-noise ratio greater than 1, and the Andromeda Galaxy is probably close to a detectable threshold, which we use of signal-to-noise ratio 7. And so for circular binaries, this is what it looks like. However, if we look at eccentric binaries, things get a little more complicated. So the general idea with this is that if you have a circular binary, it really only predominantly emits at one frequency. And it does have contributions from some other frequencies, but you can think of this as a soloist with some backing vocals. However, when you start looking at an eccentric binary, you're really looking at an entire choir of different singers, all singing at different frequencies. And so the plot gets a little more complicated. So if we now look at this in terms of the sensitivity curve, let's take that same point, which was at the Milky Way center and was all the way up here, and now plot it, instead of for a circular binary, for an eccentric binary with an eccentricity of 0.7. Now just plotting the n equals 2 harmonic, you can see it's much lower than it was before, because now the strain has been spread out over several different harmonics. So let's have a look what all of those look like. So now you can see there's a whole range of different harmonics. And in particular, the harmonic at which the maximum signal-to-noise ratio is really moved to the right. So I think it's interesting if we look at the signal-to-noise ratio contribution of each of these harmonics. So that's what I'm showing here in this dark line. And so you can see that there's several different important harmonics. You really start to think, where exactly should you plot an eccentric binary on here? Because you could plot it at the gravitational wave frequency that we initially had, or you could now plot it where the maximum strain is, or you could even choose the harmonic that has the maximum signal-to-noise ratio. And it's not really clear which of these is the right way to plot it, and I'm not even sure that I should be plotting it like this. But the main takeaway from this plot is that although it's starting at this frequency, once you have an eccentricity, it really moves the strain and the signal-to-noise ratio focus to a much higher frequency. And in this case, it really helps you, because you start here with this really high part of the sensitivity curve, and now the main focus is down at the minimum, and so you can detect it much, much further away, and so it's much better. But you can imagine the eccentricity could have the opposite effect. Say you started at this frequency, and the eccentricity would then push you to a higher bit of the sensitivity curve. And so really, it has mixed effects, the eccentricity. It really depends what your frequency starts at. So I think another interesting question is, what is the LISA horizon distance for these objects? So that's really, what's the furthest we could possibly detect them, given all of the other parameters? And so I'm again using this typical mass for a black hole neutron star, and I'm showing you a range of frequencies and a range of eccentricities. And so you can see this in these colors. These really bright colors here are really, really far away, and the dark colors are rather close, like nearly in the solar system. And one thing I should say is that this shaded region of the plot probably shouldn't be interpreted, simply because I have used a stationary approximation to make this plot, but I'm not sure it holds in this region, and because the frequency changes by about 1% over the LISA mission. And so maybe don't interpret too much into that particular region. But if we focus on these 3 distances that we were looking at before, the Milky Way center and these nearby galaxies, then you can see if you're to the right of this line, you can detect them in this particular parameter space. So let's say we took a binary here that had this frequency such that it was detectable in the Milky Way center, and it was a circular binary. Now, if we move it all the way up to an eccentricity of, say, 0.9, then it's detectable all the way out to the Andromeda Galaxy and even slightly beyond. And so you can see eccentricity has a really strong effect on how far we can detect these things. And you can also see what I was talking about before, where if the eccentricity gets too high and it pushes it past that minimum of the sensitivity curve, the distance starts to go down again, which I think is quite interesting. Great, so let's move on to the main results. So let's take a look at this sensitivity curve again, and now instead plot an entire Milky Way instance on the sensitivity curve. Now I should mention that this is for a simulation assuming all the binaries are circular, simply because, as I was saying before, I'm not exactly sure how we should plot them if they're eccentric. And so bear in mind that these are only circular binaries. So now if we plot all of these binaries, you can see an entire cloud of points down here with really rather low signal-to-noise ratios, considering that rather below the sensitivity curve. But these two here, these stars, are detectable. So we define detectable as above a signal-to-noise ratio of 7. And so in this particular Milky Way instance, we got 2 detectable binaries. And so if we now, instead of just doing one, run many, many simulations for many different random Milky Ways, then we come up with a distribution of the number of detections. And so what we find is that we'll find between 0 and 5 detections during the LISA mission. And the probability of getting a detection is about 50-50. But this is for solar metallicity. So if we instead move down to a much lower metallicity, say a tenth of solar metallicity, then you actually find up to 26 detections during the LISA mission, and the probability of getting at least one is near certain. So what I need to do now is really work in that metallicity distribution from the Frankel model, which I haven't done yet, and hopefully we'll then find a number that is somewhere between these two. So a common question that also gets asked is what happens if LISA is extended? What's the difference between a 4-year and a 10-year mission? So what I'm going to do here is then flip between the two plots between a 4 and a 10-year, and you'll see the signal-to-noise ratios change, and this point here will become detectable. It just gets pushed over that signal-to-noise ratio threshold of 7. And so you don't see a huge difference, but, slight. Another thing to consider is LISA isn't the only detector out there. So the mu-Aries detector has also been proposed, and that will focus on microhertz instead of millihertz. And so that may be better for detecting these black hole neutron stars. So if we now instead plot the mu-Aries sensitivity curve, it looks something like this, where you can see that lots of these points have now become much more detectable, not detectable, and this point here has actually been pushed over the threshold. And you can imagine that although this is for circular binaries, with eccentric binaries, a lot of these could then get pushed up. They don't have to go too far to get above the sensitivity curve. And so it'll be interesting to see how that develops when I fully work that in. So just a brief discussion on some planned improvements I need to work on. So as I was just saying, I need to really work in this eccentricity, which has been slightly difficult because all of the numerical integration is rather computationally expensive. And so that's been slowing down my simulations, and I'm working on that. Another thing to consider is that we haven't really used the systemic kicks here. So each of the black hole neutron stars are going to go through several supernovae, and that can result in natal kicks and Blau kicks. And this could move where they are in the Milky Way. Now, we don't think this is going to have a large effect because the kicks aren't strong enough such that they will eject them from the Milky Way. And the LISA horizon distance is pretty close to the Milky Way edge. And so it might move them around within the Milky Way, but shouldn't hopefully affect the number of detections. And then one final interesting thing to think about is physics variations. So could LISA really help us to understand binary formation physics? Because if we have different models for, say, the common envelope phase and run several different simulations, we may find that they have different numbers of detections. And when LISA comes along, we can then work out the number of detections that actually occurred and hopefully rule out some of these models. And so I'm going to be running lots of different simulations to try and work that out. And so I'll leave you with my conclusions that LISA is likely to detect a few black hole neutron stars. This result is strongly dependent on model assumptions, and we can in principle detect them all the way up to the Andromeda Galaxy. And one last thing to think about is, although LISA is likely to detect a few black hole neutron stars, we don't know whether it will be able to distinguish that they are black hole neutron stars. And so that's something that we should really think about going forward. And so I'll leave you with my email in case you've got any questions, comments, or feedback. And thank you so much for listening.